Hi, this is Stelios from the Tesseract Academy, and in this video, we're going to talk about Bayesian networks and Bayesian statistics. So our world is inherently probabilistic. There's uncertainty about many outcomes in the world, such as when will it rain, what the price of a stock will be, or when will the next military conflict take place. These are just some example questions which we can't find a way to answer them with complete certainty. And that's why we need a way to handle uncertainty. And probability is the best theory we have so far in order to control uncertainty, to express uncertainty and understand how to better control it. So probability, as most of you will probably know, is expressed in a range from 0 to 1. 0 indicating something which is impossible and 1 indicating something which is certain. Many people are familiar with the definition of probability around things such as gambling and games. However, probability can be used in many other cases. It can be used, for example, when trying to predict unique outcomes such as sporting events or elections, etc. We'll talk more about this in a second. So probability theory gave rise to statistics, and there are two approaches to probability and statistics: frequentist and Bayesian. One of the core ideas behind statistics is that we can control uncertainty by using probability distributions to express it. But before we talk about probability distributions, let's talk a bit more about the differences between the frequentist view on probability and the Bayesian view on probability. So the frequentist view on probability is that probability is seen as some kind of limit after an infinite number of experiments. And this is the definition of probability most people are the most familiar with. So let's say that you're rolling a die or you're doing some other kind of experiment. Eventually, the probability of rolling 6 on a die is going to converge to some value. In this plot here, you see 5 different experiments, and you can see for this particular experiment, all the values eventually converge around 0.2. On the other hand, Bayesian probability, the Bayesian definition of probability, defines probability as a belief that something is going to take place. And this might sound a bit weird at first, like, how can you define the belief for the probability of getting 6 on a die? However, the Bayesian definition of probability becomes easier to understand once we deal with unique events, such as election or sports games. Because treating probability in this case, something that arises from an infinite number of experiments, doesn't make sense anymore. These are unique events, so when we're talking about the probability of someone winning an election, then essentially we're describing a belief. I mentioned earlier that probability distributions are a tool that is being used in order to express and control for uncertainty. And probability distributions have some very nice properties around this. First of all, they have a very intuitive explanation if you know how to use them. And the first property is that they can arise naturally in many cases if we just make some simple assumptions. The Poisson distribution and the Gaussian distributions are examples of this. That's the first property. The second property is that they follow specific parameters. And if we can infer these parameters from a sample of the population, then we can fully express uncertainty across the whole population. This is a very powerful idea. We're not going to delve into it in much detail, but it's one of the ideas that came about a couple of centuries ago and revolutionized science, essentially. So here are some example probability distributions. This is the Gaussian distribution, which most people are familiar with. They defined on the interval of the real numbers from minus infinity to positive infinity. And it's used to express many phenomena in nature, including noise, but also things such as physical variables like the height, the weight, or IQ. Another famous probability distribution is the Poisson probability distribution, which is defined for counts of events, especially events which are relatively rare in their occurrence, such as earthquakes or arrivals of ambulances in a hospital, etc. Another famous probability distribution is the exponential. The exponential probability distribution is used to define the waiting time between events and is defined on the line of the real numbers from 0 to positive infinity. It's closely connected to the Poisson distribution because the Poisson distribution expresses the number of events and the exponential distribution can express the timing between those events. This gives rise to what is called the Poisson process. So Bayesian statistics, I mentioned earlier that they define probability as a belief. And something important about Bayesian statistics is the prior. So this is something which is absent from frequentist statistics. So there are three elements when we're performing Bayesian inference: the prior, the likelihood, and the posterior. So the prior is the probability of seeing something before we see any kind of evidence. The likelihood is the evidence, and then the two are combined to create the posterior. The idea behind Bayesian inference is that as we get more information, we update our beliefs, and then the likelihood is going to slowly overtake the prior. So talking about the prior, this might seem a bit arbitrary. So what's the prior like? What do you mean by this? So the prior in a real setting refers to any setting where expert knowledge is important. Let's say that you're testing for disease. The prior in this case could be the test's false positive rate or the proportion of people that have this disease across the population. If you're designing a system that predicts whether employees are resigning each month and you want the system to reduce the number of resignations, then you could use, for example, the proportion of old resignations as the prior. And more often than not, the knowledge we have around a domain before we even start an experiment or an implementation of a new model. But sometimes it's also data-driven. Like in sports, a useful prior can be the performance of a player in the past seasons. So if a new season starts in a game, let's say basketball, the NBA, or football, then the performance of a player in the last season is the prior, and then as more games are played, we update our prior with the performance of the most recent games. So the prior initially is a bit of a difficult concept to grasp, and in reality it's difficult to give a thorough explanation of Bayesian statistics unless we really go in depth. However, the takeaway from this is that Bayesian statistics and priors are very useful if you're working on problems where you already have some expert knowledge about and you'd like to use this expert knowledge in the model you're building.